Today we are starting chapter 13. This chapter is about electricity, current, circuits, and electrical energy. We will connect what we already know about atoms and charge to real systems like wires, batteries, light bulbs, breakers, and household circuits. Before we begin, remember that atoms are made of charged particles. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. Since electricity depends on charge, understand that these particles have the foundation for everything that we will be doing in this chapter. The atom. If an atom has the same number of protons and electrons, then the charges balance out. That means the atom has no overall charge. We call this electrically neutral. Neutral does not mean that there are no charges present. It means that the positive and negative charges cancel out to cancel each other overall. Static electricity. Static electricity is the buildup of excess charge on an object. A common example is shuffling across a carpet and then touching something metal. Electrons can be transferred from one material to another, leaving one object with extra electrons and the other with fewer. In this nice example, man shakes hand with woman and zip zap. The law of conservation of charge. Charge can be transferred, but it cannot be created or destroyed. When an object becomes charged, that charge came from somewhere else. So in any charging process, electrons are moving from one place to another, rather than being made out of nothing. And this should make sense, since these charges are likely going to be the electrons. Electrical charge. Electrical charge creates a force. That force depends on the distance and the amount of charge. When charges are closer together, the electric force is stronger. When the amount of charge increases, the force also increases. So both distance and charge size matter. You could say they are directly related. Help! I'm still stuck in the computer. Ah! But for real though, I'm stuck in the computer. Please, save me. Opposite charges attract each other, while like charges repel each other. Positive and negative charges pull together. Two positives push apart, two negatives push together. What? No. Two positives push apart and two negatives push apart. This is a basic rule that explains a huge amount of electrical behavior. Likes repel, opposites attract. Electrical field. Every electrical charge is surrounded by an electric field. An electric field is the region around the charged object where it can push or pull on other charges. Even if two charged objects are not touching, the field allows a force to act over a distance. Electrical force is also what holds chemical bonds together. In ionic bonding, remember electrons are transferred, and in covalent bonding, electrons are shared. In both cases, electric attraction is involved. This should remind us that electricity is not just in wires and outlets. It is also going to matter for everything at the atomic level. It's a very strong force. Transferring charge. Some materials let electrons move easily. These are called conductors. Metals such as copper are good conductors. Other materials hold electrons more tightly and do not allow them to move as easily. These are called insulators. Common insulators include plastic, wood, rubber, and glass. I'm made out of glass. Insulated wires. Copper is commonly used in wires because it's a very good conductor. Plastic or rubber is placed around the copper because those materials are good insulators. The conductor allows the current to move, and the insulator helps protect us from being shocked, or your house from being caught on fire. Charging by contact. Charging by contact happens when charge is transferred by touching or rubbing. The classic example is rubbing a balloon on your hair. Electrons move during the contact, leaving the objects with a different charge. You can see this man is also trapped in the computer. He will not be saved. That is, of course, because they already got him. Charging by induction. Charging by induction is different because it does not require direct contact. Instead, a nearby charged object causes electrons in a neutral object to rearrange. So the charge distribution changes because of the electric field of something close by. You can see in our picture here, going from A to E, we are charging something that is connected through a ground circuit, but not directly touching the thing charging it. And then we can make or induce a charge without having direct contact. Thunder and lightning. Thunderstorms involve very large buildups of static electricity. When enough charge builds up in the clouds, it can be discharged as lightning. Lightning is a massive electric spark. It heats the surrounding air very quickly, causing the air to expand rapidly. That sudden expansion creates the sound wave we hear as thunder. Or, as Chick Hicks would say, ka-chigga, ka-chigga. Thank you for this Cars 1 TED Talk. Electrical grounds. A ground provides a safe path for electricity to leave a system. This is important because excess charge needs somewhere safe to go. Buildings are grounded, and tall buildings may also use lightning rods to direct electrical discharge safely into the ground. You can also use a lightning rod to change a creeper into a super creeper or a villager into a witch. Do not try this with a pig, or you'll end up with a zombie pigman. Unless. Electroscope. An electroscope is a device used to detect electrical charge. It does not usually tell you the amount of charge, but it can tell you whether a charge is present by moving different parts internally. So on this version, we're going to have electrical charges up by the sphere at the top, and that changes the foils at the bottom. These are very old. Section 2, electrical current. Now we move from static electricity, where charges build up in one place, to electrical current, where charges move continuously through a path. This section is really about how electricity flows in a controlled way. Electric current. Electric current is the movement of charges in a single direction through a path. In metal wires, this is usually when electrons are moving through the conductor. The SI unit for current is amps or ampere, represented by the capital letter A. Flow of current. A helpful comparison is water flow. Water flow from high pressure to low pressure. In a similar way, electric current flows because of a difference in electrical potential, moving from high voltage to low voltage. Voltage. I hardly know him. Voltage is a difference in charge, or more accurately, a difference in electrical potential. It is what pushes charges through a circuit. Without a voltage difference, charges would not have a reason to move in one direction. The SI unit for voltage is the volt, represented by the capital letter V. Look at this. Thanks, Science Joy Wagon. Circuits. A circuit is a closed path that current follows. If the path is complete, charges can move. If the path is broken anywhere, the current stops. So for electricity to keep flowing, the circuit must stay closed. Batteries. Batteries provide a voltage difference to a circuit. They store energy as chemical potential energy and then convert the energy into electrical energy that can move charges through a circuit. It almost feels like Christmas, except I have no eggnog. Thankfully, I can just get some milk from my creature. The family enjoys their milk at the table. Little do they know it was harvested from the creature. I ran out of ketchup, so I went down to the basement. The creature cried. He knows it's time for milking. "Hey, chef," I called into the kitchen. My meal began being prepared by the creature. Thank you. Thank you. More about batteries. There are different types of batteries. Dry cell batteries are the kind that most people use in their day-to-day lives. They contain an electrode paste, a carbon rod, and zinc. Chemical reactions inside a battery create a separation of charge, which produces voltage and allows current to flow when the circuit is connected. More batteries. Wet cell batteries use liquid electrolytes and metal plates. A car battery is a common example. When the chemical reaction occurs between materials in the cell, they produce voltage. Many wet cell batteries provide about 12 volts. Differences in voltage. Batteries are not the only source of voltage. Wall outlets also create a difference, and that voltage is much greater than what small batteries provide. Common household outlets in the United States are 120 volts or 240 volts, depending on the circuit and the appliance. Why do light bulbs glow? You might ask if you're a strange young child. Inside a light bulb, current passes through, at least in incandescent lights, a very thin tungsten filament. Because the filament resists the flow of electrons, it heats up. When it gets hot enough, it glows and gives off light. So electrical energy is being converted into heat and light. Resistance. Resistance is a material's tendency to oppose the flow of electrons. The more resistance means it's harder for current to move. When resistance is present, electrical energy can be converted into other forms, especially thermal energy. The SI unit for resistance is ohm, shown in the symbol omega, or the symbol for God of War, or the symbol for Omega Ruby from the hit remake of the Pokemon game on the 3DS. The simple circuit. The simple circuit needs three basic parts. First, we need a source of voltage. It's usually a battery. Second, it needs a resistance or load, such as a bulb. And third, it needs a path for the current to travel, such as wires connecting everything together. We also sometimes like to put a switch in here, but that is not necessary to make a simple circuit. Ohm's law, your final triangle of the year. Ohm's law shows the relationship between voltage, current, and resistance. The formula is V equals I times R. Voltage equals the current times the resistance. We can also rearrange that to solve for current or resistance depending on what information we are given. Relationship. Because of Ohm's law, voltage, current, and resistance are connected. If one changes, at least one of the others must also change. For example, if voltage is increased and resistance stays the same, then current increases. If resistance increases and voltage stays the same, current decreases. Understanding a circuit. Circuits are often shown in schematic diagrams. These diagrams use symbols instead of realistic pictures. Learning the symbols helps us quickly understand how a circuit is connected and what components are included. Section 3. Electrical energy. In this section, we will move from simply describing current in circuits to thinking about how electricity transfers energy. This is where we connect electricity to real devices in the home and everyday life. Circuits. There are two major circuit types. The first is a series circuit. In a series circuit, current only has one path or loop to follow. That means every part of the circuit depends on the same single path remaining complete. Open circuit is not one of the two types of circuit. An open circuit is one where the path is broken somewhere. When the circuit is open, current cannot flow. A switch in the off position creates an open circuit. Parallel circuits. A parallel circuit has two or more paths for current to move through. This is important. because one branch can stop working while the other branch still operates. This is why we use parallel circuits in homes. Basement wiring circuit. House wiring is done in parallel, so if one device turns off, burns out, or is disconnected, the rest of the devices still work. If home wiring were all in a series, one problem could shut down everything in that line. Here you'll see we have 3 outlets that are not at least 6 feet apart. You'll see the NEC code says that they need to be further apart than that. What we do see that's positive is that this washer and dryer have their own dedicated outlet. That's great. We also see these lights have their own dedicated outlet, and this water heater has its own dedicated outlet. All true and good things. What I don't like here is it doesn't show us if this is GFCI protected, and we don't know if it's safe. Fuses and breakers. Fuses and breakers are safety devices. A fuse contains a small metal piece that melts or breaks when too much current passes through it, and then it must be replaced. A circuit breaker works differently. Heat causes a metal part to bend and trip a switch, so the breaker can be reset and reused. Cars typically have fuses, while homes have circuit breakers. Electrical energy. Electrical energy can change into other forms. It can become mechanical energy, like the spinning fan. It can become radiant energy, like the light from a lamp. Or it can become something like thermal energy from something like a space heater. This is why electricity is so useful. It can be transformed into many different outputs. Power. Remember that power is the rate at which electrical energy is converted into another form. We use the formula power equals current times voltage, or P equals I times V. The SI unit for power is a watt, represented by a capital W. Remember, some texts will use a lowercase w, and we don't know why. Practice time. The current in an electrical clothes dryer is 15 amps and is plugged into a 120 volt outlet. How much power does the dryer take? Remember, P equals IV. Here we apply the power formula. A clothes dryer has a current of 15 amps and uses 120 volts. We would multiply the current by voltage. 15 times 120 equals 1,800 watts, which is 1.8 kilowatts. We did it. Energy. Electric companies don't just charge for power. They charge for total electric energy used over time. Electric energy is found by multiplying the power in kilowatts by the time in hours, and that gives us kilowatt hours, or K, capital W, lowercase h. More practice. If a microwave runs at 1,100 watts for 10 minutes, how much electrical energy is used by the microwave? In this example, a microwave running at the specified amount of watts for the 10 minutes, we convert the watts to kilowatts first because we will be using kilowatt hours. So we would do our favorite little metric conversion, moving our decimal 3 to the left, and get 1.1 kilowatts. Then we can need to convert those 10 minutes into an hour, and 10 minutes is a sixth of an hour. So we would multiply 1.1 kilowatts times a sixth, which is an hour, to get 0.18 kilowatt hours. This shows that energy is being used. It depends on both how powerful the device is and how long it